Welcome, Axor, Galactic Observatory tonight. The journey begins in the deepest silence the universe can offer. Space looks cold, empty, and still. But the truth is far stranger than most people imagine. The darkness between the stars is not simply freezing. It is a place where heat, light, and matter obey rules so alien that even the idea of temperature begins to break apart. In this documentary, the story moves through the physics of vacuum, radiation, the eerie balance of the cosmic microwave background, and the chilling reason most of the universe rests near 2.7 Kelvin. What begins as a simple question soon opens into one of the most unsettling truths in all of science. If this channel brings the universe to life in a way that feels calm, mysterious, and unforgettable, please take a moment to like this video, subscribe, and support Axor, Galactic Observatory, so more deep cosmic journeys can continue. Far beyond the warm surfaces of planets and far beyond the bright skins of stars, the universe opens into an expanse so empty that ordinary language begins to fail. The eye imagines darkness first, then distance, then silence. But even those familiar ideas remain too human and too small for what actually fills most of the cosmos. Between one star and the next, there usually stretches a gulf of almost pure nothing, a reach of space so thinly populated with matter that the few wandering atoms within it seem more like accidents than substance. Around every galaxy there lies more emptiness than light. Between galaxies the emptiness grows deeper still, extending across millions of light years in regions where no sun rises, no air moves, and no surface waits to hold warmth. This is the true backdrop of existence, not the glowing worlds that attract attention, not the brilliant stars that dominate the night sky, but the vast intervals that separate them. The visible universe contains astonishing structures: spiraling galaxies, giant stars, clouds of dust, clusters of worlds, and black holes with gravity strong enough to bend light. Yet almost all of its volume belongs to the quiet void in between. That quiet is not a poetic quality. It is the consequence of scarcity so extreme that the familiar behavior of matter barely applies. A cubic centimetre of air near sea level on Earth contains an almost unimaginable crowd of molecules, colliding constantly, exchanging energy, pressing against skin, glass, stone, and leaf. A cubic centimetre of interstellar space may hold only a few atoms, sometimes less than one on average, spread so widely that each particle travels enormous distances before encountering another. In deeper intergalactic regions, even that faint trace diminishes further, until matter becomes so rare that the mind struggles to picture it. Space in this condition is not a windy emptiness or a frozen mist. It is a near-total absence, a domain where the substance that makes weather, breath, sound, and touch possible has nearly vanished. This emptiness dominates the universe not by force but by scale. Stars appear powerful, and they are. Galaxies appear immense, and they are. But their radiance occupies islands within an ocean whose greater truth is vacancy. The night sky seen from Earth encourages the opposite impression. It looks crowded. Thousands of visible stars scatter across darkness, and the pale band of the Milky Way suggests a packed celestial river. Yet that impression comes from viewing luminous objects across enormous depth, compressing staggering distances into a flat dome overhead. The apparent richness hides the reality that the nearest star beyond the Sun lies more than 4 light-years away, with trillions of miles of almost empty vacuum in between. Even within galaxies, where stars gather in vast numbers, they remain separated by intervals so large that whole solar systems drift through darkness with scarcely any material nearby. The universe is therefore not built as a continuous fabric of matter with occasional gaps. It is built the other way around. It is mostly gap, mostly interval, mostly room without furniture, structure, or support. The few dense places where matter collects become precious exceptions. Inside this broad emptiness, ordinary instincts lose their grip. Human life evolves inside an atmosphere, on a planet wrapped in moving air, bathed by oceans, clouds, pressure, and continuous contact with matter. Every sensation of warm and cold, every experience of wind, every memory of winter or summer depends on living within a thick local envelope of particles. Deep space offers none of that. No breath drifts there. No breeze crosses its distances. No surrounding medium presses gently or harshly against a surface. A drifting object in the void does not sit inside a cold fluid the way a stone rests in seawater or a hand rests in winter air. It exists within absence. That absence stretches across almost all known cosmic territory. The stars that appear permanent and central are temporary furnaces scattered thinly through it. Planets circle them for a while. Moons accompany those planets. Dust forms rings and clouds. Gases collect, collapse, ignite, and disperse. Yet all these dramas remain local disturbances in a universe whose larger character is astonishingly spare. In the great dark between one bright region and another, there is no atmospheric blanket, no soft mixing of conditions, no broad reservoir of nearby matter to smooth extremes. There is only distance and the faintest residue of energy crossing it. This is why the subject of cosmic cold begins not with temperature but with emptiness. Before any number can be attached to the universe, before any thermometer can be imagined, the setting itself has to be seen clearly. The universe is not a chamber filled with cold substance. It is not an endless winter. It is not a celestial version of polar air. It is a near vacuum so complete that the common idea of cold starts to unravel the moment it enters this environment. The terrifying quality of space does not arise merely from how low temperatures can become. It arises from the indifference of the setting itself. The void does not wrap around matter and steadily draw warmth away like ice water around a hand. It simply leaves matter alone with whatever energy it already has and whatever radiation happens to cross its path. That is a subtler and more unsettling condition than ordinary cold. It means that most of existence unfolds in a place that offers no comfort, no cushion, and almost no physical companionship at all. Matter gathers briefly into stars and worlds, burns, shines, cools, and disperses again, all within a framework whose dominant trait is emptiness beyond easy comprehension. The cosmic scene, taken at its largest scale, is therefore not one of abundant glowing substance, but of rare light suspended in a kingdom of near nothing. To understand how cold space really is, the mind first settles into that kingdom and remains there long enough to feel its governing truth. The true environment of the universe is not warmth, motion, or contact. It is vast separation. It is the immense dark between the lights. To understand how cold space really is, the idea of cold itself has to be stripped down to something more precise than feeling. In ordinary life, cold seems obvious. A winter morning feels cold, a metal railing feels cold, ocean water feels cold, ice feels cold. The body learns this word early and uses it with confidence because the sensation appears direct and immediate. Yet what seems immediate is already an interpretation. The body is not detecting cold as a substance or a force in its own right. It is detecting the movement of heat away from warm tissue into something that can accept that energy more easily. Skin, nerves, and brain translate that loss into a single simple judgment, and that judgment becomes one of the most familiar experiences in life. But familiarity hides what is really happening. Cold is not a thing flowing inward, it is heat flowing outward. This distinction matters everywhere, but it matters especially in the vacuum of space, where many of the normal pathways for heat loss disappear. On Earth, warm skin sits inside an active sea of particles. Molecules in air collide with the body constantly. Some arrive cooler than the skin and draw energy away. Some move off and are replaced by others. When wind blows, it removes the thin layer of air that has been warmed by the body and replaces it with colder air, increasing the rate of heat loss. Water does this even more effectively because it carries heat away faster than air. Metal feels colder than wood at the same room temperature because metal conducts heat more efficiently, allowing energy to leave the hand more rapidly. The body experiences all of these situations as versions of cold. Yet the common thread is not the presence of a special cold ingredient. The common thread is the speed and direction of energy transfer. Something around the body accepts heat, and the body notices the loss. The sensation is real, but the explanation people often attach to it is incomplete. In ordinary speech, cold is treated as though it were a positive condition, something an environment contains and then delivers. Science describes the situation differently. Temperature is a measure connected to the motion of particles, and what feels cold is usually an environment whose particles or surfaces contain less thermal energy than the body. Heat flows from greater concentration to lesser concentration. The body sits at a temperature that must be maintained within a narrow range to keep cells functioning well. Whenever the surroundings provide an easier path for energy to leave than for energy to stay, the sensation of cold emerges. This helps explain why the same air temperature can feel different under different conditions. Humidity matters, wind matters, wet skin matters, direct sunlight matters. A sunny winter day can feel milder than a cloudy one at the same measured temperature because solar radiation adds incoming energy, even while cold air continues drawing energy away. A shaded wall can feel cooler than the sunlit sidewalk beside it because the balance of incoming and outgoing heat differs. The body is always participating in an exchange, not reading a simple fixed property. Once this is understood, a crucial shift becomes possible. The question is no longer what cold is made of, because it is not made of anything. Cold is a name given to a reduction, a deficit, an outward flow of energy from warmer matter toward cooler matter or toward open space. That makes the concept strangely dependent on context. A surface that feels cold to a human hand may be warm compared with the night air. Water that feels icy to bare skin may be comfortable to an animal adapted to colder seas. Even the word freezing can mislead. It suggests a uniform state, but in reality it only identifies a temperature threshold for a particular substance under specific conditions. Water freezes at one familiar point under ordinary pressure on Earth. Other materials freeze at different points. Carbon dioxide solidifies under colder conditions. Nitrogen liquefies and boils far below the temperatures of everyday winter. What human beings call very cold occupies only a tiny warm corner of the full thermal range nature permits. This matters because the language of cold evolved for survival on one world, not for describing the universe. It works well in forests, deserts, houses, and oceans. It works far less well once matter becomes sparse, and the usual contact between bodies and surroundings breaks down. The body expects cold to arrive through touch, air, wind, moisture, and conduction. Space removes almost all of those familiar mediators. No stream of freezing molecules rushes across the void. No cosmic wind scrapes heat from exposed skin in the ordinary sense. No broad surrounding medium exists to carry warmth away by contact. That is why many intuitive answers about space turn out to be wrong. They borrow earthly sensations and project them outward into an environment where the terms no longer operate in the same way. The human mind wants to ask whether space feels colder than Antarctica, colder than liquid nitrogen, colder than the deepest polar night. Yet those comparisons belong to places with matter, places where molecules crowd together and exchange energy efficiently. Deep space is a different condition entirely. Before reaching that difference directly, however, it helps to recognize how much of ordinary thinking depends on confusing sensation with mechanism. A winter wind is not cold because it contains coldness as an ingredient. It is cold because it accelerates the loss of heat. An ice cube is not full of cold in any physical sense. It is a body with lower thermal energy than the hand that touches it. The same logic extends through thermodynamics. From rooms and seasons to laboratories and stars, energy moves, particles jostle, surfaces emit and absorb radiation, systems drift toward balance. Cold names the side of that process where energy is scarce relative to a warmer reference point. This makes cold more ghost-like than it first appears. It is powerful in experience, yet empty as a physical substance. One cannot pour cold from one container into another the way water can be poured. One cannot isolate a particle of cold. One can only reduce heat, transfer heat, prevent heat, or lose heat. Once the mind begins to accept this, space becomes less like a frozen region waiting to be measured and more like a challenge to the everyday meaning of temperature itself. The body's old instinct still whispers that darkness and emptiness must automatically mean cold. In a certain limited sense, that instinct points in the right direction, but it reaches that conclusion for the wrong reason. The next step is to see why temperature, as people usually understand it, depends on matter being present in the first place, and why that dependence makes the vacuum of space one of the strangest thermal environments in all of nature. Temperature in the ordinary scientific sense belongs to matter. It does not belong to emptiness by itself. This is the point where intuition usually begins to slip, because the word temperature feels so universal that it seems applicable to any place at all. A room has a temperature, water has a temperature, iron has a temperature, a cloud has a temperature. It seems natural, then, to imagine that space must also have one, as though the vacuum between stars were a kind of invisible fluid waiting to be measured. But temperature, in its standard physical meaning, describes the average energy of motion among particles within a substance. In a gas, it refers to how fast molecules move, collide, rebound, and share kinetic energy. In a liquid or solid, the picture changes in detail, yet the basic requirement remains the same. There must be matter present. There must be particles to carry energy and to express that energy through motion or vibration. Remove almost all particles, and the concept does not disappear entirely, but it loses the everyday meaning that makes it so useful on Earth. The problem is not that scientists cannot speak about temperature in very thin gases or in radiation fields. They can. And they do. The problem is that the vacuum of deep space contains so little matter that the familiar mental image of a surrounding environment with a definite temperature becomes misleading. A thermometer works on Earth because it is immersed in a medium rich with particles. Air molecules strike it continuously. If the thermometer is colder than the air, energy flows into it until equilibrium is reached. If it is warmer than the air, energy flows out. In either case, the instrument settles toward the temperature of the surrounding medium because there is enough matter present to enforce that balance through constant microscopic contact. Place the same thermometer in deep space, far from stars and planets, and the situation changes completely. There is no thick swarm of molecules pressing it toward a common background condition. The instrument no longer reads the temperature of an enveloping substance. It mainly reveals its own balance between incoming radiation and outgoing radiation. In that sense, it becomes less like a passive observer and more like an active participant in its own measurement. Its colour matters, its surface finish matters, its orientation matters, its internal heat matters. Two nearby thermometers with different coatings could settle at different temperatures in the same region of vacuum, not because space around them has changed, but because each object handles energy differently. This alone shows how strange the vacuum is compared with earthly environments. Temperature usually feels like a property that belongs to a place. In deep space, it becomes more accurate to say that temperature belongs to the objects present in that place and to the energy exchanges they experience. The surrounding emptiness contributes almost no matter of its own. Even where there is some gas between stars, the density is so low that ordinary contact-based heat exchange becomes negligible. The atoms are simply too sparse. A few particles drifting through a cubic centimetre do not create the kind of thermal bath that air creates in a room or water creates in a lake. The interval between collisions can be enormous. The average particle may travel huge distances before interacting with another. This makes the usual concept of ambient temperature feel thin and abstract. It still has meaning in carefully defined contexts, especially when describing the gas itself, but it no longer maps onto sensation or into the common picture of a cold surrounding medium. A person standing in a cold field on Earth is immersed in matter at every moment. A spacecraft crossing interstellar space is not immersed in that way at all. It is surrounded primarily by absence, by near vacuum, by a setting in which thermal contact through matter has almost vanished. This is why the question, how cold is space, contains a hidden trap. It treats space as though it were a substance with a single simple number attached to it. That framing works for oceans, lakes, weather systems, and rooms, because those are material environments. It works poorly for regions where matter is almost missing. The deeper truth is that emptiness itself does not behave like air with a lower reading on a thermometer. Emptiness does not press, buffer, circulate, or conduct in the familiar way. It allows other processes to dominate, above all the exchange of radiation. This does not make the thermal story simpler, it makes it more subtle. On Earth, a warm body surrounded by colder air tends to cool through collisions with nearby molecules, while moving air and moisture alter the rate. In space, with almost no nearby matter to collide with, that pathway fades. The body or object then depends mainly on radiation for losing heat, and on external radiation sources for gaining it. The absence of matter therefore does not erase temperature from the universe, but it does change where temperature meaningfully resides. It lives in stars, dust grains, spacecraft hulls, moons, suits, rocks, and atoms. It lives in radiation fields that objects absorb. It does not live in the vacuum itself as a simple ordinary background the way cold air surrounds a winter traveller. This matters so much because human imagination keeps trying to restore the missing medium. It wants space to be filled with something, even if that something is called cold. But the more accurate picture is harsher and stranger. The vacuum offers almost nothing at all. It has no thermal kindness and no thermal cruelty in the human sense. It does not actively freeze. It does not carry coldness inward. It simply fails to provide the dense matter needed for ordinary thermal contact. As a result, the familiar relationship between body and environment breaks apart. Matter no longer sits within a surrounding sea that easily dictates its temperature. Instead, each object becomes a thermal island, exchanging energy according to its own position, composition, and exposure. In dense earthly settings, temperature feels communal because countless particles connect everything continuously. In deep space, temperature becomes local and conditional, tied to the object and its energy budget rather than to a substantial medium around it. Once this is seen clearly, the vacuum ceases to resemble an ultra-cold atmosphere and begins to look like something more radical. It is not merely cold air reduced to an extreme. It is the near removal of the stage on which ordinary temperature usually acts. The next step is to examine just how little matter remains in the spaces between stars, and why that extreme thinness makes the void feel less like an environment and more like an almost total subtraction of one. The spaces between stars are not completely empty, but they come close enough that the distinction matters more in theory than in ordinary imagination. Interstellar space contains traces of matter, yet the amount is so slight that the word gas, while technically useful, can mislead the mind into picturing something denser, softer, and more continuous than what is really there. In a laboratory, a gas fills a chamber with countless molecules crossing tiny distances and colliding constantly. In the interstellar medium, atoms and molecules are scattered so thinly that a single cubic centimetre may contain only a few particles, and in some regions even fewer than one on average. That means the volume of a sugar cube drifting between stars may contain less matter than the emptiest vacuum chambers humans can build on Earth. And it maintains that thinness not for minutes or hours but across stretches of space so vast that light itself needs years to cross them. This is matter reduced to a whisper. It remains present enough to shape galaxies over long spans of time, enough to seed new stars under the pull of gravity, enough to carry magnetic fields and cosmic rays, enough to absorb and emit faint radiation, but not enough to behave like anything the senses recognize as an environment. There is no mist hanging in the void. There is no invisible river pressing against a surface. There is only sparse drift, occasional collision, and immense distance between particles. Most of the interstellar medium is hydrogen, the lightest and most abundant element in the universe. Some regions contain neutral hydrogen atoms. Other regions contain ionized gas where energetic starlight has stripped electrons away. Denser pockets allow molecules to form, including molecular hydrogen and more complex compounds mixed with dust. Yet even the denser clouds between stars remain astonishingly tenuous by earthly standards. A molecular cloud that astronomers describe as thick may still be emptier than the best vacuums produced in advanced research facilities on Earth. The language of space always carries this strange inversion. Dense often means barely there. A cloud can span dozens or hundreds of light years and still contain less matter per unit volume than the air inside a quiet room. This is why interstellar matter can remain transparent across great distances while still affecting starlight in subtle ways. It can redden light, dim light, polarize light, and slowly gather under gravity. Yet it almost never offers the kind of direct physical contact that defines life on a planetary surface. The thinness changes everything about heat. In ordinary dense gases, temperature has practical force because particles crowd together enough to exchange energy rapidly. In interstellar space, even if those particles can be assigned a temperature, they're too few to impose that condition efficiently on a solid object passing through them. A drifting spacecraft travelling between stars would not feel wrapped in gas of a certain temperature the way an aircraft is wrapped in air. The craft might encounter individual atoms moving at high speed, and those atoms may carry energy, but the overall density is so low that their thermal influence through direct collisions remains tiny compared with the effects of radiation. This is one of the strangest features of the interstellar medium. In some regions, the sparse gas can be described as extremely hot, especially where energetic processes have accelerated particles to high speeds. Yet because the density is so low, an object immersed in that gas may not heat quickly at all through contact. The usual everyday intuition breaks again. A medium can have a very high particle energy and still fail to roast an object if there are too few particles to deliver that energy at a meaningful rate. By the same logic, a medium can be described as very cold and still fail to drain heat quickly if there is almost nothing there to collide with the object in the first place. Density, not just temperature, governs the practical experience. The near emptiness between stars therefore strips thermal language of its easy certainty. It is not enough to ask how energetic the particles are. One must also ask how many there are, how often they interact, and whether their presence is substantial enough to matter to a passing body. Usually, compared with the radiation, the answer is very little. Dust adds another quiet ingredient to this sparse realm. Tiny grains of carbon-rich and silicate material drift through interstellar space, often mixed into clouds of gas. These grains are important far beyond their size. They absorb starlight, re-emit energy in infrared wavelengths, help certain chemical reactions occur on their surfaces, and contribute to the raw material from which future stars, planets, and possibly life-bearing systems eventually arise. Yet dust, like gas, is rare on average. A beam of light may travel enormous distances before meeting enough grains to be visibly dimmed. The famous dark lanes across the Milky Way are not dense walls in the human sense. They are simply regions where enough dust has accumulated along the line of sight to block some of the background glow. Their power lies in scale, not thickness. Interstellar space therefore becomes a lesson in how the universe can remain active while being almost empty. Gravity works across the silence. Radiation crosses it without needing a medium. Magnetic fields thread through it. Shock waves from exploding stars travel across it. Atoms ionize, recombine, and drift. Molecules form in shielded cold regions. New stars begin in the slow collapse of clouds that would seem impossibly diffuse by earthly standards. Yet none of this changes the central fact that the space between stars is still, in practical terms, a vacuum of extraordinary purity. It is not the opposite of emptiness. It is emptiness with faint ingredients. That faintness is what makes the question of space temperature so slippery. There is matter there, but too little to support the common picture of an ambient thermal bath. There are particles, but too few to give ordinary contact its familiar role. There is gas, but stretched almost beyond the meaning of the word. Once this becomes clear, the mind begins to understand why heat in space cannot be approached with everyday ideas alone. The thin gas between stars does not restore normal experience. It only shows how near to complete absence the cosmos usually is, and how thoroughly that near absence hands the thermal story over to deeper physical processes. Once the emptiness of space and the thinness of the matter within it become clear, the next part of the puzzle follows naturally. Heat can move from one place to another in only a few basic ways, and the vacuum of space removes most of them. On Earth, this rarely attracts much attention because all three major pathways of heat transfer operate at once almost everywhere in daily life. A warm mug cools in the hand, on the table, and in the surrounding air. Sunlight warms a stone. The stone passes energy into the air touching it. Moving air carries some of that warmth away. Human skin loses heat to clothing, to air, to water, to wind, and also to the surrounding walls through invisible radiation. The world of everyday experience is a crowded thermal conversation, and each pathway overlaps with the others so completely that they are easy to confuse. But space is a ruthless simplifier. It strips the situation down and reveals which methods truly depend on matter and which do not. The first pathway is conduction. Conduction is heat transfer through direct contact. When one object touches another, energy passes through their microscopic structure from the warmer side to the cooler side. A bare foot on stone, a hand on metal, a pot on a stove. All of these involve conduction, in solids. The particles do not travel freely through the material the way gas molecules do, but they vibrate, jostle, and pass energy along. Some materials conduct better than others. Metals are efficient conductors because their internal structure allows energy to move quickly. Wood is less efficient, which is why wood and steel can sit in the same room at the same measured temperature, while the steel feels colder to the touch. The steel is not more full of cold. It simply draws heat away faster. Conduction is therefore intimate. It requires matter touching matter. In deep space, that requirement usually fails at the first step. A drifting object has nothing pressing against most of its surface. No air clings to it. No surrounding fluid waits to accept heat. The path that feels so immediate on Earth becomes nearly irrelevant in the open vacuum, unless the object is touching another object directly. The second pathway is convection. This is heat transfer through the bulk movement of a fluid, usually a gas or liquid. Warm air rises because it becomes less dense. Cooler air sinks. Water heated from below begins to circulate. Weather, sea breezes, boiling water, cloud formation, and even many of the comforting effects of indoor heating depend on convection. A fan cools skin mostly by changing how air carries heat away. Ocean currents move thermal energy across vast distances, inside stars and planets. Convection can transport energy through enormous layers of fluid material. Yet convection requires a medium that can flow. It needs a fluid with enough density for warmer and cooler regions to move past one another and exchange energy through circulation. In the vacuum of space, there is no such surrounding fluid. No air rises. No cool stream sinks. No current passes across exposed surfaces. This entire mechanism, so important on Earth, falls silent in open space. The absence is profound because convection is one of the main ways environments soften thermal extremes. It mixes conditions together. It spreads energy around. It smooths sharp differences. Without it, boundaries between hot and cold can become harsh and abrupt. The third pathway is radiation. Radiation is the transfer of energy by electromagnetic waves. Unlike conduction and convection, it does not require matter. A warm object emits thermal radiation simply because it has a temperature above absolute zero. The human body emits infrared radiation. Walls, floors, clouds, and deserts do the same. The sun radiates across a broad range of wavelengths, carrying energy through the vacuum between star and planet without needing any gas to support that journey. Radiation alone can cross empty space freely. This makes it the dominant thermal pathway in the cosmic void. A spacecraft far from any atmosphere gains heat when it absorbs sunlight or reflected light from a nearby world. It loses heat when it emits infrared radiation outward into space. Its thermal state depends on the balance between those flows, not on a surrounding bath of air. This is the crucial turning point in understanding why space is so different from any cold place on Earth. On Earth, conduction and convection are almost always present, even when radiation also matters. In deep space, only radiation remains significant across open surfaces, and this changes the entire meaning of a thermal environment. The void itself does not actively cool by contact. It does not conduct heat away the way cold water does. It does not convect heat away the way moving air does. It simply allows radiation to pass without obstruction. That may sound passive, and it is. Yet the consequences are severe, because radiation can create intense heating, where light arrives, and relentless cooling, where outgoing energy is not replaced. A surface in sunlight can climb to high temperatures. A nearby surface in shadow can plunge far lower. The difference between the two can develop over very small distances because nothing in the vacuum smooths the contrast. Earth's atmosphere usually prevents such abrupt thermal cliffs. Air mixes sunlight-warmed and shade-cooled regions. Wind carries heat. moisture redistributes energy. Space does none of this. The missing pathways matter as much as the remaining one. This is why it is not enough to say that heat moves differently in space. 2 out of the 3 great modes of transfer lose almost all practical force in the open vacuum. The universe does not merely become colder or emptier than Earth. It becomes thermally selective. It leaves radiation in command. Once radiation takes command, everything depends on exposure, absorption, emission, angle, reflectivity, color, and time. An object's temperature no longer emerges from simple contact with its surroundings. It emerges from an energy ledger, from what arrives as electromagnetic energy and what departs the same way. The stillness of space is therefore deceptive. Beneath that stillness, thermal change remains active, but its logic is no longer the logic of weather, ice, breath, or wind. It is the logic of light meeting matter across an abyss. That is why the vacuum feels so alien to common sense. It has not merely become colder than ordinary environments. It has dismissed 2 of the rules by which ordinary environments usually work, leaving only the most subtle and far-reaching pathway behind. With conduction nearly absent and convection effectively removed, radiation becomes the ruling language of heat in space. It is the only major pathway that can cross the vacuum without assistance, the only one that moves energy between separated bodies through pure emptiness. This makes light far more than illumination. It becomes warmth, pressure, information, and fate. Every object with a temperature above absolute zero emits electromagnetic radiation, even if no eye can see it. A warm rock emits mostly infrared radiation. Human skin does the same. A planet radiates. A moon radiates. A spacecraft hull radiates. The hotter the object, the more energy it emits, and the shorter the typical wavelength of that emission becomes. This principle does not pause when matter becomes sparse. In fact, it becomes more important in the vacuum, where so few particles exist to carry heat by contact. Radiation remains as the one unavoidable exchange. Matter in space constantly announces its energy state by the light it emits, and constantly responds to the light it absorbs. That is why the thermal reality of the cosmos depends so heavily on who is shining, what is exposed, and how surfaces handle incoming and outgoing energy. The Sun is the most immediate example near Earth. It floods nearby space with radiant energy that crosses roughly 93 million miles of vacuum without needing any medium at all. That energy arrives at a planet, a moon, an asteroid, or a spacecraft, and can be absorbed, reflected, or transmitted depending on the nature of the surface it meets. A dark, rough surface tends to absorb more. A bright, reflective surface sends more away. A polished thermal blanket on a spacecraft is not merely decoration, it is a survival strategy. By controlling how much light is taken in and how much infrared radiation is allowed to escape, engineers shape temperature without relying on air, wind, or flowing water. Radiation turns surface properties into critical thermal decisions. Color, texture, angle, and composition acquire enormous importance because in the vacuum there are fewer other ways to correct a bad balance. This is one reason the thermal behavior of a body in space can seem so counterintuitive from an earthly perspective. A white surface may stay cooler in sunlight than a black one because it reflects more incoming solar energy. A material that emits infrared efficiently may cool more quickly in darkness. A surface turned toward the sun may become dangerously hot while another just centimeters away. Facing shadow, sheds energy and plunges towards severe cold. The vacuum does not average these conditions together. Radiation allows them to coexist side by side. This gives space an almost theatrical quality, with light and darkness acting not as mere visual states, but as competing thermal powers. Sunlight in space is harsh because there is no atmosphere above to scatter, soften, or filter it. On Earth, air and clouds modify the sun's energy before it reaches the ground. In orbit or on an airless world, direct sunlight arrives with a starkness that makes exposed surfaces heat quickly if they absorb enough of it. The darkness of shadow is equally severe because shadow in space is not filled with the gently mixed air of the surroundings. It is a region where direct radiant input has suddenly fallen away while emission continues. Energy keeps leaving, yet little arrives to replace it. This simple imbalance can create extraordinary thermal contrasts. Radiation, therefore, does not merely warm or cool, it defines local reality. Whether a surface bakes or freezes depends on its personal conversation with light. Even the faint glow of nearby objects matters. A spacecraft near Earth may absorb sunlight directly, reflectance from Earth's clouds and oceans, an infrared radiation emitted upward by the planet itself. Near the Moon, the lunar surface contributes radiation of its own. Near a giant planet, the thermal influence of that planet can become important. Deep in interstellar space, far from strong local sources, the incoming radiation diminishes until only the faint universal background remains. The object then slowly settles toward a far colder equilibrium. In every case, radiation writes the script. It is not merely one influence among many. It is the governing exchange in a setting stripped of most alternatives. This dominance also reveals why the phrase "the temperature of space" remains misleading. Space itself is not sending cold through the vacuum. Radiation sources and radiation sinks are establishing an energy balance for each object. The empty region between them is the stage, not the actor. The sun does not need air to warm a spacecraft. The spacecraft does not need air to cool itself by emitting infrared light. A drifting rock does not need a surrounding breeze to lose energy. The vacuum permits these radiative transactions to happen cleanly, almost ruthlessly, without the buffering role that dense matter would normally play. In that sense, radiation is both elegant and unforgiving. It respects no comfort zone. It only follows physics. The amount absorbed depends on flux and surface response. The amount emitted depends on temperature and emissivity. If more comes in than goes out, the object warms. If more goes out than comes in, it cools. This is the core thermal truth of the void. It transforms the idea of cosmic cold from a simple number into a dynamic balance. The universe is not waiting everywhere with one uniform chill. It is offering a sparse, often brutal arrangement of radiative circumstances in which each body must find its own temperature. Once this is understood, space begins to look less like a giant freezer and more like a place where light and absence together decide everything. Radiation becomes the great organizer of thermal existence beyond atmospheres. It reaches across nothingness, carries the memory of stars, reveals the energy of worlds, and determines whether matter glows warmly, cools quietly, or drifts toward the deepest cold the cosmos can provide. Once radiation takes command of heat in space, every object becomes the center of its own thermal story. This is one of the hardest ideas to accept because it runs against the ordinary habit of assigning one temperature to one place. In everyday life, a person enters a room and asks how warm the room is, not how warm each object in the room is likely to become according to its color, orientation, and exposure. That shortcut works because air surrounds everything densely and pushes many surfaces toward a shared condition. A table, a wall, a book, and a cup of water may differ somewhat, especially in sunlight or near a heater, but they remain tied together by a thick atmospheric medium that constantly redistributes energy. In space, that common medium is nearly absent. A thermometer, a rock, a satellite panel, and a helmet visor do not automatically converge toward the same simple background state. Each one absorbs and emits radiation according to its own physical nature, and each one therefore settles into a temperature determined by its own balance sheet, rather than by immersion in a common thermal sea. This turns every object into a kind of isolated accountant of energy. The object records what arrives, subtracts what departs, and lives at the temperature that the balance permits. A thermometer placed far from stars and planets illustrates the point clearly. On Earth, a thermometer is usually thought of as reporting the air temperature around it. In deep space, there is almost no air to report. The instrument mainly absorbs whatever radiation strikes it and emits its own radiation outward. If it is painted black, it may absorb more incoming energy. If it is highly reflective, it may absorb less. If one side faces a star and another side faces darkness, the geometry matters. If internal electronics generate heat, that too changes the result. The number displayed by the instrument is not the temperature of vacuum as a medium. It is the temperature of the instrument under those specific radiative conditions. Another thermometer nearby, built differently or oriented differently, could show a different reading. This is not a flaw in either instrument. It is a revelation about the environment itself. The vacuum does not impose one easy answer. It permits individual thermal outcomes. The same logic applies to natural bodies. A dark asteroid rotating slowly through sunlight may grow very hot on its day side and become extremely cold on its night side. A bright icy surface may reflect more sunlight and remain cooler under direct illumination than a darker rocky surface nearby. A spinning object averages its exposure differently from a tidally locked object that keeps one face turned toward a star. A hollow spacecraft panel behaves differently from a dense metal block. Thin materials can heat and cool quickly. Massive structures change more slowly because they store more thermal energy. Composition matters because some materials absorb certain wavelengths better than others. Surface texture matters because roughness affects reflectivity and emissivity. Even shape matters because it determines how much area is presented to radiation sources and how efficiently energy can be emitted away. In the vacuum, these details are not minor refinements. They are the main factors that determine temperature. This is why thermal design becomes such a central part of space engineering. A spacecraft is not simply sent into a cold place and then protected with generic insulation. It must be designed as a system that will encounter sunlight, reflected light, planetary infrared glow, internal waste heat, eclipse periods, and deep shadow, sometimes all within a single orbit. Solar arrays, radiators, instruments, fuel lines, batteries, and crew compartments may each have different thermal needs. Some components must shed heat efficiently, others must retain it. The craft cannot rely on surrounding air to equalize conditions. It must arrange surfaces and materials so that the right amount of energy enters and the right amount leaves from each region. One side may be coated to reflect solar input. Another may be designed to radiate internal heat outward. Heaters may be installed not because space is uniformly cold, but because certain parts will otherwise fall below safe operating limits whenever incoming radiation drops. The International Space Station provides a vivid example. It circles Earth through cycles of sunlight and eclipse, experiencing constant shifts in radiative input. Its enormous radiator panels do not cool the station by blowing heat into surrounding air. They cool it by emitting infrared radiation into the vacuum. The station's systems, experiments, electronics, lighting, and human occupants generate heat that must be carried to those radiators and released. At the same time, some external components spend long periods in shadow and require electrical heating to prevent damage from excessive cold. The structure therefore contains both ways of fighting the vacuum at once, rejecting excess heat here, preserving scarce heat there. The lesson is clear. The temperature of the environment alone is not the useful question. The useful question is what each component is exposed to and how each component manages energy. Natural objects follow the same rule without planning. A rock on the moon, a dust grain in a nebula, a comet nucleus in the outer solar system, and a probe crossing interstellar space all carry their own thermal identities. They do not sit inside a uniform cosmic bath. They negotiate with radiation continuously. They become warm where energy arrives and cool where energy escapes. Their temperatures emerge from circumstance rather than from a simple background label. This is why the phrase space is cold, while not entirely wrong in outcome, is deeply incomplete in mechanism. It skips over the fact that the vacuum itself is not the active cold agent. The vacuum merely withholds the dense material context that would otherwise dominate heat transfer. In that withholding, it leaves each body responsible for itself. The universe becomes a place where objects are thermally alone. They receive light, they emit light, and from that exchange their temperatures are written. Every surface becomes its own little climate. Every exposed body becomes an argument between incoming and outgoing radiation. This is the strange freedom and danger of the void. It does not force one communal temperature on everything within it. It leaves matter to find its own. If every object in space writes its own thermal story through radiation, then there must still be some lowest chapter toward which that story tends when almost all local influences fade. Far from stars, far from warm planets, far from bright dust clouds and active galaxies, an isolated object does not cool forever without limit. It approaches a flaw, a baseline set not by surrounding matter, but by a faint field of radiation that fills the universe itself. This field is the cosmic microwave background, the oldest light still travelling through space, the dim remnant of a much hotter early cosmos. It arrives from every direction with astonishing uniformity, and gives the universe a thermal minimum of roughly 2.7 Kelvin above absolute zero. This number is often presented as the temperature of space, and while that is an oversimplification, it captures an important truth. Any object left alone in deep space long enough, with no stronger source of radiant energy nearby, will eventually cool until the energy it emits matches the energy it absorbs from this ancient background glow. At that point, the object reaches equilibrium. It does not become the temperature of vacuum in a strict thermodynamic sense, because vacuum itself is not a material substance with an ordinary temperature. Instead, the object reaches the natural radiative resting point set by the universe's faintest omnipresent light. That is why 2.7 Kelvin matters so much. It is not merely another low number on a scale of cold. It is the thermal floor of the cosmos in the absence of more local drama. On a human scale, it is almost impossible to picture. Absolute zero marks the theoretical point at which thermal motion reaches its minimum allowed state. Nature never quite arrives there. The third law of thermodynamics makes perfect zero unattainable through any finite process. Yet the cosmic background lies so close to that boundary that for ordinary imagination the difference feels vanishingly small. Water freezes at a temperature that, when measured from absolute zero, seems almost warm by comparison. Liquid nitrogen, famous for flash freezing in laboratories and demonstrations, boils at 77 Kelvin. Liquid helium, one of the coldest widely used substances on Earth, boils at a little above 4 Kelvin. The cosmic background sits even below that, colder than liquid helium, colder than nearly all naturally occurring conditions humans ever encounter, colder than the most severe winter ever recorded on Earth, by an amount so large that familiar comparisons begin to lose meaning. This is why the background floor changes the whole emotional scale of cosmic cold. What counts as unimaginably cold on Earth is still vastly warmer than the passive baseline toward which the universe drifts when left to itself. And yet even this flaw is not the whole story, because it is not simply a local environmental accident, it is the fading afterglow of creation. The ancient universe begins in a state of extraordinary heat and density. In its earliest moments, matter and radiation exist together in a compressed, energetic plasma so intense that no atoms can remain intact. As space expands, that radiation spreads out and loses energy. Much later, when the cosmos cools enough for electrons to join atomic nuclei and form neutral atoms, light can finally travel freely through space. Those photons do not vanish. They continue moving in every direction across the universe for billions of years. As the universe keeps expanding, their wavelengths stretch. Shorter wavelengths become longer ones. Visible and infrared light from that early epoch is gradually redshifted into microwaves. With the stretching comes a decline in effective temperature. What was once the glow of a hot young cosmos becomes an all-sky microwave bath at just 2.7 Kelvin. This is the remarkable origin of the cold floor. It is not emptiness by itself that sets the baseline. It is ancient radiation thinned and cooled by cosmic expansion over nearly the entire history of the universe. The result is a background so faint that no human eye can detect it, yet so universal that every isolated object must eventually reckon with it. In deep interstellar or intergalactic darkness, this radiation becomes the last quiet source of incoming energy that remains when brighter neighbours are gone. A drifting body emits infrared radiation outward because it is warmer than the background. As it cools, the rate of emission changes. Meanwhile, it continues to absorb the tiny inflow from the microwave background. Eventually, the outgoing and incoming amounts balance. Cooling stops. The object has reached the thermal default of the cosmos. This makes the cosmic microwave background less like a dramatic heat source and more like a whisper that nothing in the universe can fully escape. It is the low, steady murmur beneath all louder thermal conversations. Near a star, its influence is overwhelmed. On a planetary surface, local conditions dominate. Inside a galaxy rich with radiation fields, dust, and energetic events, it becomes almost irrelevant for daily thermal behavior. But in the deepest reaches, where local light fades and matter grows scarce, the background reasserts itself as the final reference point. There is something unsettling in that. The universe is not only mostly empty, it is mostly arranged so that, absent special local heating, matter drifts toward a temperature barely above the coldest state physics allows. Warmth becomes local, cold becomes universal. Heat requires a nearby story, a star, an atmosphere, an active interior, a recent collision, a radioactive core, a dense cloud collapsing under gravity. Remove those stories and the cosmos relaxes towards silence, and 2.7 Kelvin. This is the first truly reliable number in the discussion, not because it gives vacuum an ordinary temperature, but because it reveals the radiative flaw to which lonely matter tends. It is the calmest answer the universe can offer when almost everything else has gone dark. The cold floor of the modern universe makes sense only when set against the heat from which the universe begins. The cosmos is not born cold and then left unchanged. It begins in a state so hot and dense that every familiar comparison fails long before the description is complete. In the earliest fraction of a second, there are no stars, no planets, no atoms, and no empty black distances between things. Space itself is young, rapidly expanding, filled everywhere with energy packed into an almost incomprehensible intensity. The event commonly called the Big Bang is not an explosion inside pre-existing space. It is the beginning of expanding space. together with the matter and radiation that fill it. In that first extreme state, the universe is not organized into objects. It is a seething plasma of fundamental particles and radiation, a continuous hot environment in which the conditions for ordinary matter do not yet exist. Temperature at this stage is not a local weather-like property. It is a universal condition. Everywhere is hot because everything is still compressed into a much smaller and denser cosmos than exists today. This is the key to the later story of cold. The universe cools because it expands. As space stretches, the energy density of radiation falls. Photons are redshifted to longer wavelengths. Matter spreads out. Interactions that were once unavoidable become less frequent. The whole cosmic environment changes because the stage itself is growing larger. Cooling is therefore not an accident or a local event. It is the direct thermal consequence of expansion. During the earliest moments, the temperatures are so high that the distinctions familiar to later cosmic history have not yet settled into place. Matter and radiation remain tightly coupled. Particles collide constantly. Energies are enormous. Over brief but decisive intervals, the universe changes character as the temperature drops through successive thresholds. Quarks become confined into protons and neutrons. A short time later, within the first few minutes, conditions become suitable for the formation of the lightest atomic nuclei. Protons and neutrons combine in a burst of early nuclear chemistry, often called Big Bang nucleosynthesis. Hydrogen nuclei remain the most abundant outcome because a single proton already counts as hydrogen. Some deuterium forms. Helium nuclei form in substantial amounts. Tiny traces of lithium also appear. Then the temperature falls further, and that early nuclear window closes. The young universe does not continue fusing nuclei indefinitely. It expands too quickly, cools too quickly, and becomes too diffuse for that first brief episode to last. By the time those first minutes pass, the broad chemical groundwork for later cosmic structure is already established. Most ordinary matter now exists in the form of hydrogen nuclei and helium nuclei, but the universe is still far too hot for neutral atoms. Electrons remain free. Radiation remains intense. Light still cannot travel freely across great distances because charged particles scatter photons again and again. The universe is therefore full of light and yet opaque. This is one of the strangest conditions in cosmic history. A modern mind associates light with visibility, but the early universe contains so much interacting radiation and so many charged particles that visibility in the ordinary sense is impossible. Every direction is bright, yet nothing can be seen through the glow because photons are repeatedly interrupted in their motion. It is a luminous fog without stable surfaces, horizons, or stars. As expansion continues, the cooling persists patiently and everywhere at once. There is no outside cold flowing inward. There is no cosmic winter descending on the early plasma. There is only the steady decrease in density and temperature produced by expanding space. This gives the history of the universe an almost musical downward scale. At first, the note is impossibly high. Then it drops, not into silence, but through stages that permit new forms of matter and new relationships between matter and radiation. Each lower temperature unlocks a different kind of structure. The early universe, therefore, does not simply become less hot. It becomes more articulated. It gains the ability to support stable combinations that intense heat had previously prevented. This is why cooling is one of the deepest creative forces in cosmic history. A universe that remained at its original temperatures could not produce atoms, stars, planets, chemistry, oceans, or organisms. The fall in temperature is not merely a loss. It is the condition that allows complexity to emerge. Even so, At this stage in the story, the universe remains overwhelmingly hostile to anything like the later calm of space. For hundreds of thousands of years after the first minutes, temperatures stay high enough to keep matter in plasma form. Electrons move freely rather than attaching to nuclei. Radiation still dominates the thermal environment. The cosmos remains smoother and more uniform than it will later become, though tiny fluctuations in density already exist and will eventually matter greatly under gravity. What matters here is the persistent bond between light and charged particles. The young universe is filled with energy that cannot yet stream freely across it. Photons are trapped in a ceaseless pattern of scattering. Matter and radiation still share one coupled thermal existence. There is not yet a dark sky, not yet transparent emptiness, not yet a true background radiation field in the later sense, because radiation has not yet been released into long, unhindered journeys across space. The cooling continues, however, with perfect indifference and perfect consistency. Expansion keeps stretching the cosmos. Temperatures keep falling. The great heat of the beginning does not vanish suddenly. It thins, weakens, and transforms over immense spans of time. The later cold of the universe is already hidden inside this process, not as a separate event, but as the far future of the same expansion that begins at the start. In that sense, every patch of near-frozen interstellar darkness belongs to a story that starts in universal fire. The 2.7 Kelvin background of the modern cosmos is the faint residue of a heat once so intense that no atoms could exist. The coldest common condition in today's universe is therefore not the opposite of the Big Bang. It is its distant descendant, the final quiet note of an ancient blaze that has been cooling ever since space first began to grow. At roughly 380,000 years after the beginning, the long cooling of the universe reaches one of its most consequential thresholds. Until this era, matter and radiation remain bound together in a dense luminous partnership. Free electrons move everywhere through the plasma, and those free electrons scatter photons so efficiently that light cannot travel far without being deflected. The universe is bright but opaque, full of energy yet closed to long, clear vision. Then the temperature falls enough for a major transition to occur. Electrons lose sufficient energy to become captured by atomic nuclei. Protons combine with electrons and form neutral hydrogen atoms. Helium nuclei capture electrons as well. This event is commonly called recombination, though in a strict sense it is the first large-scale combination of electrons and nuclei rather than a reunion of partners that had previously existed in atomic form. The name matters less than the effect. Once matter becomes electrically neutral on a broad cosmic scale, photons are no longer scattered at anything like the previous rate. Suddenly, the universe changes from an opaque plasma into a transparent sea of gas. Light, which has been trapped in endless collisions, finally begins travelling freely across space. This moment is one of the deepest turning points in cosmic history, because it creates the oldest light that can still be observed. The photons released into unhindered motion during this transition continue their journey through the expanding universe for billions of years. They carry with them a record of the conditions present when the cosmos is still very young compared with its present age. The release of that light does not illuminate stars or galaxies, because those structures have not yet taken shape in the familiar later sense. Instead, it fills the whole universe with a nearly uniform glow. If an observer could somehow exist in that era and survive its conditions, the sky in every direction would appear luminous rather than dark. Not with the brilliance of a nearby star, but with a broad, dim radiance spread across the entire heavens. There would be no empty black night in the modern sense, only the lingering thermal light of a universe that has finally become transparent enough for photons to travel unimpeded. This is the origin of the radiation later known as the cosmic microwave background. At the time of release, however, it is not microwave radiation. Its effective temperature is still around 3000 Kelvin, which places much of its energy in the visible and near-infrared range. The universe at this stage glows with the muted warmth of a cooling furnace, rather than the frigid whisper it will later become. The crucial process that changes that glow is not local cooling in one region or another. It is the continued expansion of space itself. As the universe grows larger, the wavelengths of the freely travelling photons are stretched along with it. A photon that once carries the energy characteristic of visible reddish light is gradually redshifted into longer and longer wavelengths. Longer wavelength means lower energy. Lower energy corresponds to a lower effective temperature. Over billions of years, the once warm all-sky glow is thinned and cooled by the expansion of the cosmos until it reaches the microwave range. This is why the background radiation seen today is so cold. It is not newly produced cold light. It is ancient hot light, stretched, diluted, and transformed by cosmic history. The transparency of the universe after recombination also opens the way for later structure to emerge more clearly. Once radiation decouples from matter, gravity can shape the slight irregularities in density that are already present. Regions with a bit more matter begin, over immense timescales, to gather more strongly. The later formation of stars, galaxies, and clusters depends on this earlier release, yet at the moment itself, the dominant significance is quieter and more direct. The universe becomes a place where light can cross vast distances without being constantly interrupted. Space begins to resemble the cosmos later generations recognize, not because it is already populated with mature galaxies, but because transparency has arrived. The dark intervals between future structures become possible only after the original glow is allowed to stream away. The irony is profound. The universe gains darkness by setting light free. As photons travel outward through the growing cosmos, their energy falls. What once fills all of space with a visible thermal haze slowly fades beyond biological sight. The modern black sky is therefore not evidence that ancient light vanished. It is evidence that ancient light survives in a form too cold and stretched for human eyes to detect. The night remains faintly luminous in microwaves even when it appears empty. This is why the cosmic microwave background is not merely another astronomical signal among many. It is the preserved afterglow of the moment when the universe first becomes transparent. It is both a relic and a witness. It confirms that the cosmos is once hot, dense, and nearly uniform, and it reveals how deeply expansion has altered that original state. The 2.7 Kelvin flaw discussed later in cosmic history is therefore born here, though it will take billions of years of additional stretching to reach its present value. At the time of a last scattering, as this release of light is sometimes called, the universe is still warm enough to glow like heated matter. Only through the patient work of expansion does that glow become the near-absolute cold background of the modern cosmos. This makes recombination one of the quiet revolutions of existence. No dramatic explosion marks it. No sudden visible rupture divides before and after in a human sense. Yet the thermal meaning of the universe changes decisively. Light stops being trapped. Space becomes transparent. The ancient radiance begins its long cooling voyage. From this point onward, the cosmos carries within itself a memory of its early fire, a memory that does not stay bright, but thins into the cold whisper that later sets the resting temperature of the deep dark between the stars. Long before satellites map the sky with exquisite precision, the first modern glimpse of the ancient cosmic afterglow arrives almost by accident. The discovery does not begin with a search for the oldest light in the universe. It begins with an unwanted noise. In the middle of the 20th century, radio technology grows increasingly sophisticated, and large antennas are built to study communication signals with greater sensitivity. Among them stands a horn-shaped antenna in New Jersey, designed to reduce stray interference and measure faint radio sources with unusual care. Two researchers working with this instrument notice a persistent hiss in their data, a faint excess signal that refuses to disappear. It remains present no matter where the antenna points. It does not rise and fall with the time of day. It does not vanish with changes in season. It seems not to belong to any city transmitter, any nearby source of interference, or any defect they can easily identify in the equipment. The signal appears to come from every direction at once. That universality is the clue. A local source would shift or weaken. Instrumental contamination might reveal itself through mechanical investigation. Yet this soft thermal noise persists with a stubborn impartiality, as though the sky itself were glowing at a low temperature everywhere equally. The researchers examine the system carefully. They calibrate the antenna. They consider atmospheric effects. They inspect the structure for contamination. Even the mundane possibility that nesting birds and residue inside the equipment might be corrupting the measurement is taken seriously and addressed. The hiss remains. What at first seems like an annoyance slowly reveals itself as a message from cosmic history. At nearly the same time, theorists are working from the implications of the hot early universe model and realize that if the cosmos begins in a dense, hot state, then some remnant radiation should still exist, cooled by expansion but not erased. That ancient radiation, if it fills all of space, ought to appear as a nearly uniform thermal background at only a few degrees above absolute zero. The unwanted hiss and the theoretical expectation meet. The noise in the antenna is not random static. It is the whisper of the early universe, the cooled afterglow of the epoch when matter and radiation first separate into the transparent cosmos that follows. This recognition transforms a technical puzzle into one of the most important discoveries in modern cosmology. The significance lies not only in detecting a faint background radiation, but in the exact character of that radiation. It is present in all directions with remarkable uniformity. The early universe, at the time the light begins its free journey, must therefore be extremely even in temperature and density on large scales, with only tiny variations. That uniformity becomes one of the central pieces of evidence for the broad picture of cosmic evolution from a hot, dense beginning. Yet science rarely rests on a single detection. Once the background is recognized, increasingly refined observations follow. Instruments placed above Earth's atmosphere gain special importance because the atmosphere itself absorbs and emits microwave radiation, making ground-based measurements more difficult. Space-based observatories provide a cleaner view. These later missions do more than confirm the existence of the microwave background. They reveal its spectrum and its minute irregularities with astonishing precision. The spectrum matters because a hot, dense early universe should leave behind radiation with the form of an almost perfect black body, meaning an ideal thermal distribution determined only by temperature. When measurements show that the background matches this pattern with extraordinary fidelity, the evidence becomes far stronger. It is not merely that there is microwave glow in the sky, it is that the glow has exactly the thermal signature expected from an early universe, once filled with radiation in equilibrium. The temperature is pinned down with increasing accuracy until the value near 2.7 Kelvin becomes one of the best established numbers in cosmology. The tiny variations matter just as much, though for a different reason. The cosmic microwave background is not perfectly smooth. It contains minute fluctuations from place to place, differences so small that they require delicate instruments and careful analysis to reveal. These slight irregularities are the seeds of later structure. Regions that are marginally denser than average will, over immense spans of time, attract more matter through gravity. From such subtle beginnings come galaxies, galaxy clusters, and the large-scale web of cosmic structure. The background, therefore, does not simply tell a story of smooth, ancient fire cooling into uniform cold. It also preserves the faint pattern from which later complexity grows. A map of the microwave sky becomes a kind of fossil record, showing not stars or planets directly, but the conditions from which all later luminous structures emerge. There is a quiet beauty in this. The coldest common radiation in the modern universe turns out to be one of its richest archives. The very field that sets the deep thermal floor for isolated objects also serves as a memory surface, recording the shape of primordial conditions with incredible subtlety. It reminds the modern cosmos that its vast cold is not empty history. It is cooled history. The ancient afterglow is therefore both baseline and evidence. It tells every lonely body in deep space what temperature it may eventually approach when all stronger influences disappear, and it tells science what the universe is like when it is less than 1,000,000 years old. The same radiation that now seems faint and almost powerless in local thermal matters near stars or planets once dominates everything. Its modern weakness is itself the proof of how long the universe has been expanding and cooling. By finding the background and then measuring it ever more precisely, cosmology gains something rare, a direct observational bridge between the present cold universe and its incandescent beginning. The discovery of the afterglow does not merely add another object to the catalogue of astronomy. It reshapes the meaning of the sky. The darkness above ceases to be truly dark. It becomes lined everywhere with ancient microwaves, too cold to see, too faint to feel, yet precise enough to reveal the temperature, history, and early structure of the universe itself. Once the cosmic background has been recognized as the faint thermal floor of the universe, the local harshness of space becomes easier to understand. The modern cosmos is not uniformly cold in practice, because local radiation sources create pockets of intense heating against a background of profound chill. The most dramatic examples appear wherever direct sunlight meets unprotected matter, and then suddenly gives way to shadow. On Earth, this contrast is softened continuously by the atmosphere. Air absorbs, scatters, and redistributes energy. A shaded wall remains cooler than one in direct sunlight, yet the difference is moderated by moving air, by the surrounding warmth of nearby surfaces, and by the fact that the sky itself still contributes diffuse light. Even in a desert, the transition from light to shade is usually noticeable but not absolute. In the vacuum of space, that buffering system is absent. Sunlight falls with uncompromising clarity, and shadow removes that direct input with equal decisiveness. The result is a thermal boundary far sharper than ordinary experience prepares the mind to expect. A surface exposed to full solar radiation can become intensely hot because the incoming energy arrives unfiltered, and because there is no surrounding air to carry part of that energy away by convection. If the material absorbs strongly and emits inefficiently, the temperature can climb rapidly. A nearby surface turned away from the sun, however, may continue radiating its own heat outward while receiving little or no direct replacement. Because the vacuum does not circulate warm matter into the dark region, the temperature there can fall to severe lows. This means that in space the line between light and shadow can act not merely as a visual edge, but as a thermal cliff. The human body experiences shade on Earth as relief. In open space, shadow can mean a swift move toward dangerous cooling if no system exists to compensate. Sunlight can mean equally dangerous heating. The peril lies not in one simple coldness, but in the lack of moderation between extremes. An astronaut's suit in orbit captures this reality vividly. One side facing the sun may absorb strong radiant input and rise toward temperatures that would damage unprotected tissue almost immediately. Another side facing darkness may radiate away heat and grow bitterly cold. The suit prevents these conditions from reaching the body directly through insulation, reflective surfaces, internal cooling loops, and controlled circulation, but the external thermal contrast remains real. Spacewalks therefore occur not in a single harsh temperature, but within an environment of competing radiative demands. The suit must manage heat as actively as it manages oxygen or pressure. The threat is two-sided. Too much incoming radiation overheats. Too much outgoing radiation without enough replacement overcools. The same object can face both threats at once. This principle extends well beyond astronauts. Satellites in Earth orbit repeatedly enter sunlight and eclipse as they circle the planet. During the illuminated part of an orbit, solar energy pours into exposed surfaces. During eclipse, that input vanishes while emission continues. Components heat and cool through every cycle. Engineers must ensure that batteries, instruments, fuel lines, and structural materials remain within safe limits under both conditions. Even small variations in orientation can matter. A panel angled slightly differently toward the sun may absorb significantly more energy. A shaded sensor may cool past its intended operating range unless heaters support it. The environment is not thermally uniform for even a single orbit. It changes with every passage through light and dark. Planetary shadows make this more dramatic near large bodies. Earth casts a significant shadow into space. The Moon does the same, though without an atmosphere to add any diffuse glow. Space near an airless world can therefore contain abrupt transitions where radiant energy changes sharply over distance. The vacuum itself offers no assistance in softening those transitions. There is no planetary breeze carrying warmth around the terminator, no ambient medium redistributing heat. The effect is especially stark where surfaces remain long in either light or darkness. Slowly rotating bodies or tidally locked worlds can develop profound temperature contrasts between regions, with persistent sunlight and regions that seldom or never see it. In all these cases, the vacuum behaves with the same indifference. It does not amplify extremes through active freezing or active heating. It merely refrains from smoothing them. That refusal is enough. The absence of air, water, or other dense matter means radiation can impose its logic directly. This helps explain why the popular image of space as simply freezing misses the deeper danger. Freezing is only one possible outcome, and not even the most immediate one if the object is in strong sunlight. The real danger is exposure without mediation. A body in space lives at the mercy of its radiative circumstances. Where light arrives intensely, heat accumulates unless reflected or carried away internally. Where light disappears, cooling proceeds unless internal energy or stored heat can offset it. The background temperature of the universe remains low, but local radiative geometry determines what an object actually experiences moment by moment. This is why a shadow in space is not comparable to a shaded place on Earth. On Earth, shadow still exists inside an atmosphere and above a warm surface that continues to radiate and convect energy. In space, shadow can resemble a withdrawal of support. It is less a cool refuge than a sudden loss of incoming energy in a setting already unwilling to provide any thermal comfort. The result is a universe in which local conditions can swing violently against a steady, faint cosmic flaw. Space is cold in the long passive sense, yet it is often thermally dangerous in a more dynamic sense, because light and darkness divide so sharply. The void becomes a place where equilibrium is fragile, where exposure matters more than intuition suggests, and where the simplest boundary of all, the edge of a shadow, can separate intense heat from severe cold with startling speed. Among all nearby examples of how vacuum and radiation create brutal thermal contrasts, The Moon provides one of the clearest and most unforgiving. It is close enough to Earth to feel familiar, yet its surface conditions reveal how profoundly an atmosphere changes the meaning of temperature. The lunar surface has effectively no atmosphere in the ordinary sense. There is no substantial blanket of gas to scatter sunlight, no weather to mix warmer and cooler air, no winds to carry heat across distances, no clouds to reflect or trap energy, and no pressure system to smooth local extremes. What remains is bare ground facing the full force of solar radiation during day, and then facing open darkness during night. Because the Moon rotates slowly relative to the Sun, one cycle of daylight and darkness lasts far longer than a day on Earth. This extended exposure gives its surface ample time to heat under direct sunlight, and ample time to cool when sunlight disappears. The result is a range of temperatures far more extreme than those common on Earth. Sunlit ground near the lunar equator can rise above the boiling point of water. The same surface, after the long lunar night takes hold, can plunge to temperatures so low that familiar earthly cold begins to seem almost mild by comparison. The contrast does not emerge because the space above the Moon possesses one simple cold temperature. It emerges because the surface absorbs radiant energy when sunlight arrives, and then loses energy by radiation when that input stops. All without an atmosphere to moderate the exchange. The regolith, the layer of fragmented dust and rock covering much of the Moon, responds directly to light and darkness. It does not share its heat efficiently with an overlying fluid because no such fluid meaningfully exists. This means the Moon serves as a planetary scale demonstration of the same principle that governs every isolated object in vacuum. Temperature belongs to matter and to the energy balance matter experiences. The vacuum overhead offers no common thermal bath. A thermometer placed above the lunar surface would not simply report the temperature of space. It would absorb sunlight if exposed, absorb infrared radiation from the ground beneath it, emit its own infrared energy outward, and settle at a value determined by all those competing influences. Change the height, change the colour, change the angle, and the reading changes. The object measures its own circumstance rather than a single ambient thermal truth. This is why the Moon is so revealing. Its familiar visibility tempts the mind to treat it like a cold desert or a barren plain, yet its thermal behaviour belongs to a more alien category. Deserts on Earth may become hot by day and cold by night, but air remains present. Convection continues. Wind redistributes energy. Even dry sand exchanges heat with a surrounding atmosphere that never fully disappears. On the Moon, the thermal logic is far starker. Light arrives, ground heats, light leaves, ground cools. There is little else to intervene. The lunar poles extend this lesson into even stranger territory. Because the Moon's axis is only slightly tilted, some crater floors near the poles never receive direct sunlight at all. These permanently shadowed regions can remain colder than almost any naturally occurring places in the inner solar system. They are sheltered from direct solar heating so persistently that water ice and other volatile materials may survive there for immense spans of time. These shadowed craters are scientifically important because they preserve records of material delivered over long ages, yet they are also thermal monuments to the power of persistent darkness in a vacuum. Nearby peaks that receive more frequent light can behave very differently. The Moon thus contains neighbouring regions whose thermal character is defined almost entirely by exposure geometry. This is not a secondary detail. It is the central rule. Other airless worlds follow similar patterns. Mercury, lying much closer to the Sun, experiences scorching heat on its sunlit side and severe cold on its night side, though its exact numbers differ because of its orbit and rotation. Many asteroids show strong day-night contrasts because they lack atmospheres and often rotate under direct solar illumination. Even small icy bodies in the outer solar system demonstrate the same fundamental law. Though their sunlight is weaker and their average conditions are colder, airless surfaces do not enjoy the thermal mercy that atmospheres provide. They stand directly in the path of radiation and directly in the path of its withdrawal. This is why exploring such worlds requires careful engineering. Landers, rovers, and instruments must survive not only vacuum and radiation exposure but also the relentless swings between local heating and local cooling. Materials expand and contract, electronics drift outside safe limits, batteries weaken, lubricants behave differently. Sensitive instruments may need insulation, heaters, radiators, and carefully timed operations to remain stable. A machine built for Earth cannot simply be placed on an airless world and expected to endure. It must be adapted to a surface where the thermal environment is not buffered by a sky. The Moon therefore teaches a lesson larger than itself. It reveals what happens when a world loses the atmospheric moderation Earth treats as normal. Day and night cease to be merely changes in light. They become radically different radiative regimes. Surface temperature ceases to track a gently shared environmental background. It begins to rise and fall according to direct exposure and emission. Every slope, crater, and boulder participates in that radiative arithmetic. The thermal violence of airless worlds is not a special oddity of one moon or one planet. It is the natural consequence of matter standing exposed in vacuum. Seen this way, the Moon is not only a companion of Earth, it is an outdoor laboratory for the fundamental truth of space. When air is removed, light and darkness stop being softened categories. They become the dominant forces deciding whether matter warms, cools, bakes, freezes, or drifts toward the deep baseline cold that waits wherever stronger local energy no longer arrives. If the Moon shows how an unprotected surface swings between heat and cold, spacecraft show how deliberate design can resist those swings without ever escaping them. A vehicle in space does not survive by avoiding thermal exchange. It survives by controlling it. This makes thermal engineering one of the quiet central arts of spaceflight. Rockets, probes, stations, suits, and landers all carry systems whose purpose is to manage the relentless radiative accounting imposed by vacuum. On Earth, excess heat can often be removed with airflow, liquid circulation open to the environment, or simple contact with surrounding matter. In orbit or deep space, those familiar conveniences vanish. There is no air to carry away waste heat from electronics. There is no breeze to cool a surface warmed by sunlight. There is no ambient medium to steady the temperature of delicate instruments. Every watt generated inside a machine must eventually leave as radiation or remain trapped, raising temperatures until materials, sensors, batteries, and processors begin to fail. At the same time, components that fall into long darkness or operate far from strong energy sources may lose heat too effectively and drop below the range where their chemistry or mechanics can function reliably. Spacecraft therefore live between two persistent dangers. They can overheat from incoming light and internal power, or they can overcool when radiation outward exceeds what they absorb. The solution is never one simple layer of insulation. It is a whole architecture of balance. Multi-layer insulation wraps many spacecraft in reflective blankets that reduce both unwanted heat gain and unwanted heat loss. These thin, metallic-looking layers work not by making the craft warm in a blanket-like atmospheric sense, but by reducing radiative exchange. Surfaces are chosen carefully. Some are polished or coated to reflect incoming solar energy. Others are designed to emit infrared radiation efficiently so that waste heat can be rejected into space. Radiator panels become especially important. A spacecraft cannot dump heat into air, so it must send that energy away as light, mostly in the infrared. Radiators provide controlled surfaces where this can happen effectively. They're often placed or oriented to avoid strong sunlight, allowing them to act as thermal exhaust ports. The International Space Station offers an especially clear example because it is large, inhabited, electrically active, and in constant alternation between sunlight and eclipse. The station's many systems, computers, lights, pumps, experimental racks, and human occupants all produce heat. In a sealed orbital structure, that heat would build continuously if it were not collected and transported to large external radiators. These radiators then emit energy into the vacuum. Without them, the station would not remain comfortably habitable for long. Yet the same station also contains components that must be protected from becoming too cold. Certain batteries, lines, seals, and instruments cannot simply be left to drift thermally with each orbital change in sunlight. They require heaters, active control, and careful monitoring. Flight controllers track thermal conditions closely, because temperature is never just a background fact in space operations. It is one of the variables that can determine mission success or failure. Spacesuits compress this engineering challenge into something that must function around a human body. A suit is not merely a pressure shell with oxygen, it is also a thermal habitat. The person inside generates metabolic heat. Sunlight may strike parts of the suit directly. Shadow may chill other parts. Internal moisture and gas circulation affect comfort and safety. To manage this, suits use layers that reflect and insulate, along with systems that move heat away from the body in controlled ways. The goal is not to make the surrounding vacuum less extreme. The goal is to prevent those extremes from reaching the wearer. A suit must therefore mediate between a warm living body and an external environment that can present fierce heating on one side and rapid radiative cooling on another. Deep space probes face a different version of the same problem. Far from the sun, incoming solar energy weakens enormously with distance. A craft journeying toward the outer planets or beyond may receive so little sunlight that keeping instruments warm becomes a primary concern. Radioisotope power systems sometimes help by providing electricity and also useful heat, but that heat still has to be routed and managed intelligently. Conversely, probes operating closer to the sun may require special reflective shields and careful orientation to survive the intense radiant flux. Missions that study the sun directly show just how powerful radiative heating can become when distance shrinks. In every region, the same principle governs. A spacecraft does not ask what the temperature of space is in any simple sense. It asks what radiation is arriving, what heat is being produced internally, what heat must be retained, and what heat must be expelled. The machine becomes a carefully tuned thermal argument against the indifference of the void. This engineering perspective also clarifies the deeper meaning of cosmic cold. The danger of space is not only that the universe can be extremely cold in its baseline state. The danger is that vacuum offers no automatic support for the temperatures complex systems require. It does not hold warmth close, it does not soften transitions, it does not carry excess heat away except through the slow and geometry-dependent pathway of radiation. A poorly designed craft can bake in sunlight or fail in darkness, not because the laws of thermodynamics become unfamiliar, but because they become exposed. On Earth, atmosphere often hides the full sharpness of those laws behind a cushioning medium. In space, design must confront them directly. Every mission that leaves the planet is therefore, in part, a mission in thermal balance. It is a deliberate effort to create a small movable island of controlled energy inside a universe whose dominant condition remains vast emptiness and near-frozen background cold. The success of such machines does not refute the harshness of space. It proves how carefully that harshness must be negotiated when matter tries to endure within it. By the time the modern universe is seen in full, one pattern stands above all others. Warmth is real, dramatic, and locally important, but it is not the default condition of the cosmos. It is the exception. Stars burn with immense power, yet each star occupies only a tiny region compared with the dark expanse around it. Planets may hold atmospheres, oceans, or molten interiors, yet each one is a minute oasis of thermal activity surrounded by distances so large that numbers alone fail to express their emptiness. Nebulae glow, galaxies shine. Accretion disks around black holes radiate with astonishing intensity. Supernovae blaze across space. But when the volume of the universe is considered rather than the brilliance of its special objects, the verdict becomes unavoidable. Most of existence unfolds in regions where matter is sparse, where local heating is weak or absent, and where isolated bodies tend, over time, toward the faint 2.7 Kelvin background left by cosmic history. The universe is therefore not a place occasionally interrupted by cold. It is a place of prevailing cold, occasionally interrupted by warmth. That reversal is the deepest answer to the question of how cold space really is. It is not merely that some places are very cold. It is that near absolute cold dominates by scale, by duration, and by indifference. The sources of warmth are islands. The sea around them is the true realm. This helps explain why the ordinary human image of the universe is so misleading. Human attention is drawn to luminous things. Eyes notice stars, not the vacuum between them. Telescopes reveal bright galaxies, glowing gas, and active worlds, not emptiness in its own right. Memory, language, and survival all focus on places where energy is concentrated enough to support visible structure. Yet concentration is not normal in the cosmic sense. It is the product of gravity fighting the wider drift toward thinning and cooling. Matter collapses into stars, stars radiate, planets form, atmospheres gather, chemistry becomes possible, and for a time warmth can linger. But all of that depends on local circumstances. Remove the star, remove the atmosphere, remove the recent input of energy, and matter begins to surrender its heat. It emits. It cools. It approaches the background. In that long arc, the universe reveals its broader temperament. It is not hostile in a personal sense. It is not trying to freeze anything. It simply does not provide the dense, protective, energy-rich surroundings that warm systems require unless special structures arise. Where such structures do not exist, the baseline takes over. What makes this terrifying is not the violence of an active attack, but the calmness of a universal absence. Space does not rush in with claws of ice. It waits in stillness while heat leaves. It offers no resistance to that departure, and almost no replacement unless a nearby source shines strongly enough. This is why the phrase "the cold of space" can finally be understood in its proper form. It does not describe a substance surrounding the traveller. It describes a condition of abandonment within a mostly empty cosmos. Conduction is nearly gone. Convection is gone. Radiation alone decides the balance, and in the vast majority of locations, the incoming side of that balance is faint. A lone object far from stars and galaxies becomes a small warm exception set inside a dominantly cold universe. Time works against that exception. Energy leaves in photons. Local warmth dwindles. Equilibrium with the ancient microwave background approaches. This is the slow rule of the cosmos. Even the great structures that seem permanent are temporary against that backdrop. Stars exhaust fuel. Planetary interiors cool. Galaxies change. Collisions, eruptions, and luminous episodes flare and fade. the baseline remains. The afterglow of the early universe grows colder still as cosmic expansion continues into the far future. If the larger story is followed long enough, the universe does not move toward richer warmth, but toward thinner radiation, greater separation, and broader dominance of cold. The present age still contains abundant stars and energetic processes, yet even now the cold already rules most of the volume. That is why the dazzling universe seen in images can give such a false impression. The bright parts are not the whole. They are highlights painted on an immense dark ground. The cosmic microwave background provides the faint universal floor. Local radiation fields provide temporary elevations above that floor. Between those elevations stretch distances that remind matter what the larger setting always is. The terrifying truth, then, is not just that space is cold. It is that cold in the cosmic sense is the natural resting state of almost everything once the temporary privileges of proximity, atmosphere, motion, and internal energy are removed. Warmth must be earned, maintained, or inherited from some nearby engine. Cold waits everywhere else, patient and nearly absolute. The universe begins in unimaginable heat, yet after billions of years of expansion, the condition that dominates almost all of its vastness is a temperature only a breath above the lowest allowed by physics. That journey from primordial fire to near-frozen silence is not a side story. It is the main thermal biography of the cosmos. The stars write bright chapters within it, but the dark between them carries the longer text. In the end, the true environment of the universe is not the heat of suns. It is the immense cold between them, and that cold is not rare, remote, or exceptional. It is the background condition against which nearly every brief flame of cosmic warmth must struggle to exist. The vast dark between stars remains still. No wind crosses it. No air waits there. No gentle medium rises to hold warmth in place. Matter drifts through that silence, carrying its own brief store of energy, shining for a time, cooling for a time, and gradually settling toward the faint universal glow that creation leaves behind. The old fire of the beginning has not vanished. It has thinned, stretched, and faded into a whisper spread across all directions. That whisper now lingers at 2.7 Kelvin, a quiet flaw beneath every warmer story. The bright parts of the cosmos continue their work. Stars burn, planets turn, dust gathers, light crosses impossible distances, yet around all of it lies the greater truth of near-empty space, patient and immense. Warmth appears as a local grace, not a permanent law. It belongs to stars, to atmospheres, to interiors, to motion, to recent light. Cold belongs to the long intervals where those gifts do not reach. In those intervals, the universe reveals its deeper character, not cruel, not kind, but indifferent and vast. And so the mind comes to rest with a simpler picture. Space is not cold like winter air. It is colder in a stranger way. It is the absence of almost everything that makes warmth easy to keep. It is the long radiative surrender of heat into a dark that does not answer back. It is the slow settling of lonely matter toward the oldest light in existence. The cosmos begins in fire, but most of its great body now sleeps near absolute zero, quiet beneath the afterglow of its own beginning.